the audience for assisting to my presentation. So this is a joint work with Professor Jetro from UFI. So I'm going to be talking something very simple about a work we developed by the end of last year. So we call it Holomorphic integrated vertex superalgebras. So where's the motivation for that? So the motivation is that by the year about 2017, there is a work from Jethro, Steven Moller, and Niels Scheinauer proving or studying holomorphic graded vertex algebras. If you have a holomorphic graded vertex algebra, it's like this. It turns out you can obtain properties about that vector algebra by studying this V1 part. So trying to classify the possible V1 parts will give me information about this vector algebra. That's that work I'm talking about. So they did a little trick, and they found about, if my memory isn't wrong, 223 possibilities for this V1, and then it was reduced actually to 69. So no more spoilers. That's the motivation. What we try to do is, well, can we do the same thing or try to do the same thing now in the super case? Okay? And that's the work I am presenting today. So I will be, this presentation will be as simple as possible. I will be just recalling the basic results I will need from the theory of Lie superalgebras, so we avoid the temptation of just blindly using Lie algebras results, which aren't true here, and which kind of complicates up the analysis. Then I'll talk a little bit about vector superalgebras, and then finally we get in the main part when we talk about the problem and more likely how do we proceed, how do we solve it, and what is next to solve. So this initial part will be super easy. So for probably you already know that. That's a Lie superalgebra. It's exactly the same theme as a Lie algebra, but this time you take a super vector space, okay? You have this condition because it's a superalgebra, and you have this sign condition. You have this super skew symmetry and the super Jacobi identity. There's no mystery with this definition. So the results I'm going to need. Well, now is when things start behaving not quite as Lie algebra. And it is the killing form. The killing form has an analogous definition, but this time I use the super trace. Okay? It's an invariant, again, super symmetric, and a consistent form. Now, the problem is this. And this is a big difference from the case of Lie algebras. The killing form of a simple Lie superalgebra might be degenerating. Even more, it might be 0. So that's going to be a problem in the future. By the future, I mean in about 5 or 6 slides for now. So fortunately, we still have a result like we have in usual Lie algebras, that if the killing form is not degenerated, I can decompose algebras, finite dimensional algebras, into irreducible ones. Okay? I'm going to call an algebra of classical if the G1 part is a complete reducible G0 module. And we have the following result. A finite dimensional Lie superalgebra with a non-degenerating killing form is always of classical type. Okay? So, locally for us, The job of classifying all superalgebras is already done due to Cox works, and simple superalgebras follow in the following categories. The classical one with the non-degenerated Killing form, which had the algebra of state A, B, C, D, in these cases specifically. The ones with vanishing Killing form, and the non-classical types with vanishing Killing form. I'm not going to waste time trying to define this. The only one I'm going to define is BMN, because it's the one I'm going to lead later, and it is an octosymplectic Lie superalgebra with this definition. Okay? You take a bilinear, super bilinear form, and you define the orthosymplectic algebra like this. That's just basic definition of theory of Lie superalgebras. So let's go into vertex superalgebras. So what is a vertex superalgebra? Well, the definition is almost the same as a vector algebra. So in this case, I have, instead of a vector space, a super vector space, I have a distinguished vector. I'm going to call it the vacuum vector. I have an state fields corresponding function, and I have the very same actions. But in this case, for example, here, when I put this in the locality action, this means the super commutator instead of the commutator. Okay? So I'm going to say that a conformal structure on a super vector algebra is a vector who has this Virasoro-like structure. And I'm going to ask that this decomposition into eigenspaces will have finite dimensional eigenspaces. So a conformal vector algebra, I'm going to call it CFT type if I have a case like that. All the negative part is 0. I have nothing here. And this part has dimension 1. Okay? So in this case, it can be proved that if I have a CFT type vector superalgebra, then I can define on B1 a structure of Lie superalgebra. In that case, B1 was a Lie algebra. In this case, it will be a Lie superalgebra using simply the zero product. Okay? So our goal now will be to find all possible Lie superalgebras I can put into B1 for a specific class of supervector algebra, which I'm going to define right away. So I'm going to say that a vector algebra is a C2 cofinite if the subspace spanned by the -2 products have finite codimension. And we have the following results. Okay? If I have an integer-graded formal vector superalgebra, and if it is simple, conformal field type, and this condition, L1 up by 0 on B1, then this defines a non-degenerated invariant bilinear form. And by invariant, in this case, we mean this equation. So I'm going to call the vector superalgebra as contragradient if it possesses a form like this one. And we are finally in the position to tell what a holomorphic C-graded vector superalgebra actually is. It's a self-contragradient C2 cofinite rational, and the irreducible ordinary V module is the adjoint module of V. So what's the problem we studied? Well, classify integer-graded vectors integrated superalgebra, holomorphic integrated vector superalgebra, and a specific central charge. Okay? So, as I told you, the trick here is compute all the possible V1 that might appear there. So, one of the first things you are able to prove is that the central charge will be, it must be a multiple of 8. So, you only have to study case C equals 8, C equals 16, C equals 24, and so on. And that's what we tried to do. We went up to 24. So, this is the main result we got. And it's for the case C equals 24. In the case of C equals 24, we got the following. If we have a holomorphic integrated vector superalgebra, then of central charge 24 and superdimension different from 24. And why is this superdimension different from 24? This superdimension is different from 24 because this one, the killing form might vanish. And this is the case when superdimension is equal to 24. Okay, so in this case, we analyze what should be V1, and we get that it is decomposed as a direct sum of simple least superalgebras, and this simple least superalgebra, or the actual even least algebra, or Lie algebras, or Lie superalgebras of type B0n, which are orthosymplectic Lie superalgebras. Moreover, we were able to create a list of all possible versions for all possible decompositions. Let me be precise here. All possible decompositions that might appear as V1, and we got a list that is huge as hell, 1,332, but at least it's less than infinity. Well, that's what we got until now. So for the case, okay, let's see how we prove it. So the idea to prove it was the following. The first thing is to use the fact that if superdimension is different from 24, then the killing form of V1 is not degenerated, and therefore it must decompose into simple Lie superalgebras. Then we prove this formula, okay? Relating the superdimension of this V1 part, the Cox-Lever, and the dual Coxeter number. We found a bound for this possible superdimension, and finally, we played with the computer and created a script to compute all possible decomposition for V1. That's why we got that ugly number of 1,332. So until now, we have this. For the cases central charge equal 8 and central charge equal 16, well, we did almost the same procedure. We found a similar formula. We found bounds, and we compute V1. And analyzing V1, we were able to conclude that there is nothing new when you pass from the vector algebra world of holomorphic integrated vector algebra to the super case. Okay, every holomorphic integrated vector superalgebra of central charge 8 or 16 must be even, and that's the minor result. So what is the next step, or what are the sequential problems we have from this? Is clearly enough. The first one, huge one, the elephant in the room, is reduce that ugly number. Second problem is what happens when the killing form vanishes. We have a case we are still not able to tell anything about it. And this is also a problem. We still have no non-trivial, and let me clarify what I mean with non-trivial example of holomorphic integrated superalgebra. And by not trivial, I mean something that is not purely even. Okay? So, and the super ambitious goal will be classify holomorphic integrated superalgebras at a certain central charge. That will be the most. That will be my main goal. Yeah. That's it. So, I didn't waste so much of your time. Question? Sorry? Any idea of? It's probably not. I don't have, I still don't have a number to tell you. For example, look at this case. In this original paper, they have 223, right? And they end up with 69. If I'm not wrong with 69, it's a number close to this. So most of them are not achievable cases. But in this case, I still do not have. I'm quite sure that the number should be at least a third of those ones, at least a third. Okay, that analysis, for example, it reproduces already the case they already know. The case, for example, a vectors algebra is an example of a vector superalgebra. It's an even one. So all of them will appear again in that analysis. But no, I suspect that the number should be at least a third of that, or even less. Or even could be worse. It could be that there are nothing at level 24. It won't make this result false, and it will be even a greater result, a great result. If at level 24 there is nothing new, and then we will try to prove maybe there aren't at any level, at any certain charge, maybe there aren't any super holomorphic integrated vector superalgebras. Yeah, but this is, for example, in this case, we don't even have a good example. So, okay, we define what it is. We try to extend the notion from vector algebra to vector superalgebra, and we start working and decide what will we get. Okay? This is a typo there. What will we get? Let's try analyze V1 and see let's see if we can do what we did was almost reproducing every step we did for they did because I wasn't in that project. They did for the purely even case, and we tried here with super case. We have to do some minor changes. For example, the case of super dimension equal 24 that we don't know anything about it. We have to tiny adjust some definition to make this work, but that's what we got into now. Question?
Can you get some holomorphic LBOS, Lex? Can you get some holomorphic BOS, Lex?
No.
They are decalculated.
Yeah. So it's what you could try to do is take one of those and spectral flow, right, to make the model weights become integers, but then you destroy self-contribution property.
What I mean is the method we have to construct super vectors and holomorphic vectors algebra no longer works, or at least we don't know an analog to that, to the super case. Okay?
I know one nice example. They are complex experiments, but they are not rational.
Right.
There are only one model, but negative.